Hello and welcome back. Today we're going to continue our studies with stoichiometry and we're going to look at volume to volume stoichiometry. So we're going to be dealing with gases. Last video we talked about mass to mass stoichiometry. So if you're given so many grams of one substance, how many grams of some other substance will that make? And just a quick reminder, we normally went from grams to moles, from moles to moles, and moles back to grams. Well, we're going to do about the same things now, we just have a new conversion factor to look at. So let's go ahead and look at that conversion factor. 1 mole of any gas at standard temperature and pressure will equal a volume of 22.4 liters. So if I have 1 mole of hydrogen gas at STP, it will take up a volume of 22.4 liters. If I have 1 mole of oxygen gas, it will take up a volume of 22.4 liters. If I have 1 mole of carbon dioxide, sorry, that's a 2, it will take up a volume of 22.4 liters. Now, standard temperature and pressure is, the temperature is 273 Kelvin and the pressure is 1 atmosphere. Atmospheres are just a measurement of pressure. Normally 1 atmosphere is basically sea level. There are other units out there such as torrs, and later on we'll talk about how you convert back and forth between those units. We already went over how to convert from Celsius to Kelvin in the first unit. So keep in mind in a problem, if it does not say STP or it's assumed it's STP, you need to make absolutely sure this is the temperature and this is the pressure. Otherwise, these conversion factors will not be valid. If it is not standard temperature and pressure, the gas will not take up that amount of volume and you cannot use this. At this level during this unit, pretty much everything is going to be STP. But once you get to a unit on gas laws, they might start throwing in other temperature and pressures. Now you're probably thinking, how can all these things take up the same volume? Well, basically, the particles are very far apart. So even though they have different molar masses, they will be about the same volumes. And what I mean is, these might all have the same volumes, but they will have different weights. So if I have a liter of CO2, it will be heavier than a liter of hydrogen. This is why they put hydrogen and helium in blimps. I mean, they don't put hydrogen in blimps anymore. If you remember back to the Hindenburg, which basically blew up because it was hydrogen. Now it's all helium. But those are lighter than air gases, so these do have different weights. Now let's look at conversion factors before we get started. We know 3 right now. We know 1 mole of any gas at STP is 22.4 liters. We know that 1 mole of any substance has 6.02 times 10 to the 23rd representative particles. So it could be atoms, could be molecules of that substance. We know that 1 mole of a substance will equal its molar mass in grams. So if I want 1 mole of hydrogen, I will go to the periodic table and it will weigh 1.01 grams of hydrogen. Using these conversion factors, and when I say conversion factor, really what that means is it's a relationship between 2 units that will help us convert between units. Using these conversion factors, I can solve pretty much all the stoichiometry problems I'm going to get at this level. So let's begin. If I have 15.008 liters of hydrogen gas, which are consumed at STP, how many moles of hydrogen fluoride would be formed? Well, I will start in my upper left-hand corner and put 15.008 liters of H2. And I need to convert this to moles. That's always a good first step. Well, I now know that 1 mole of any gas at STP, so hydrogen gas, equals 22.4 liters. So if I do this math, I will now know how many moles of hydrogen gas I have. So this is the exact same step in mass to mass stoichiometry, but instead of grams right here, I have liters. Okay, now I want to convert my moles of hydrogen to moles of hydrogen fluoride. I do that by building a ratio. I look at my two givens, hydrogen gas, and I want to know how much hydrogen fluoride. So 3 moles of hydrogen gas, 3 moles of H2, will equal 6 moles of hydrogen fluoride. That's my ratio that I put in this column here. And look at this, the units cancel. That's what I'm looking for. The moles of hydrogen will cancel. That's why I put moles of hydrogen on the bottom. Now, if I just go ahead and do this math, because it wants my answer to be in moles, I will get 1.34 moles of hydrogen fluoride, and that will be my answer. So let's look at the units. Liters of hydrogen, moles of hydrogen, moles of hydrogen. I'm left with 6 moles. I'm left with moles of hydrogen fluoride. So 15.008 times 1 divided by 22.4 times 6 divided by 3. Here's my answer. Let's go ahead and do the next one. In order to produce 3.50 grams of nitrogen gas, how many liters? So they're kind of throwing us a little bit of a curveball here, which is what they love to do in these worksheets. We have a little bit different question. We have grams of nitrogen, not liters, but we want liters of nitrogen fluoride. Now it does say STP, so we don't have to worry about that. So just like in mass to mass, 3.50 grams of nitrogen. Well, I know 1 mole of nitrogen will equal 28 grams. Now, where did that number come from? That's the molar mass. If we go to the periodic table, nitrogen is 14.007 grams for 1 mole, which I find right here. So if I took 14, I'll just say 14. That's how much 1 mole of nitrogen is, but I have N2, so it's times 2. So 28 grams. Now yet again, I will construct a ratio. I have nitrogen, but I want nitrogen fluoride. So there's a 1 here. If there's no number, this coefficient is 1. 1 mole of nitrogen gas equals 2 moles of nitrogen fluoride. But I want my answer in liters. I need a volume. If I did this step, I will just have moles of nitrogen fluoride. So I need to convert moles of nitrogen fluoride to liters. But it is a gas. All these are gases, so 1 mole of nitrogen fluoride. Sorry, I should have been saying nitrogen trifluoride. But anyway, is 22.4 liters. Of nitrogen trifluoride. So if I look at my units, grams, cancel, moles, cancel, moles, cancel, and I'm left with liters. And if I do the math, I would get about 5.6 liters of nitrogen trifluoride. All right, we're making some progress. I hope we're feeling a little bit confident by now. Let's go ahead and do a few more. You know, practice makes perfect in chemistry, really. I can't stress this enough. You really need to be doing, if you did 5 or 10 problems like this a day for a month, Trust me, you would just know it so well. It's just the practice. You got to put in the time. So we're moving on. We have the same equation. There should be gas right here, but they're all gases. If I have 188.608 liters of nitrogen, which are formed at standard temperature and pressure, how many liters of hydrogen fluoride would be produced at the same time? So I have 188.608 liters of nitrogen gas. Yet again, let's convert that into moles. 1 mole of nitrogen gas equals, and this is liters, so 22.4 liters of nitrogen. Let's look at N2 and hydrogen fluoride. So 1 mole of N2 is equal to 6 moles of hydrogen fluoride. Now I want to go back to liters. 1 mole of hydrogen fluoride equals 22.4 liters. This is why I really stress that you should write these units in. I notice sometimes students don't do it, but I really stress that you probably should do it, because now we know. Let's go check and see if the units cancel. Liters of nitrogen, liters of nitrogen. Moles of nitrogen, moles of nitrogen. Moles of hydrogen fluoride, moles of hydrogen fluoride. I'm left with liters of hydrogen fluoride, which is what I want. If you don't write these units in, you don't know where you messed up. Maybe you wrote something wrong. Maybe you have the wrong ratio. So it's hard to check. So you really should do that. Get in the habit of doing that. Now, if I do this math, I end up with 1,136.65 liters. So a lot of hydrogen fluoride. Okay. You have 482.8 grams of nitrogen trifluoride are consumed. How many molecules? Aha! They're throwing us for a loop again. Don't they like that? They just love doing that. And this is just going to mess people up, because they're going to look at them and be like, what? I have no idea what they're talking about. But we've done problems just like this when we did representative particles. So chemistry is one of those subjects that builds on previous knowledge. And unfortunately, when you get to stoichiometry, if you don't know some of that previous knowledge well, it starts to become much more difficult. So let's convert to moles. I have grams. I can't use my liters. I know 1 mole of nitrogen trifluoride equals about 71 grams. Now, where did I get that? From the periodic table. Remember, nitrogen is about 14.007 to be exact. Fluorine is 18.998 grams per mole times 3, because I have 3 of them. I also feel like you should get in the habit of writing out, if you're doing a molar mass, writing out your little calculations on the side, making sure you put N equals, F equals, and then doing the math properly. Because I also see people just sort of rounding it off vaguely on the periodic table and just sort of adding it up in their head. And hey, I appreciate the fact that you can do this math in your head, but in the end, it leads to little mistakes. And that little mistake will make you get the whole problem wrong. If you write it out right here and you pay attention to detail, you will not get the molar mass wrong. And also write out the entire molar mass. At the end, you can use your significant figures to then round off your answer. Okay, now we need to go to moles of hydrogen. So let's construct our ratio. We have 2 moles of nitrogen trifluoride will equal, and I want to go to hydrogen, 3 moles of hydrogen. And I don't want to go to grams. I don't want to go to liters. I want to go to molecules. So 1 mole of hydrogen gas will have 6.02 times 10 to the 23rd molecules of hydrogen gas. Now, if I do this math, I will get an answer of 6.13 times 10 to the 24 molecules of hydrogen gas. Okay, a couple more questions and we'll be done. I wanted to show you this question because this is where they start trying to be tricksters. Those chemistry teachers just like to pull tricks. They just want to see if you're paying attention. They're just a bunch of meanies. Now, this is a gas. This tells me the state that this substance is in. This is a gas. So, chlorine gas. This is a gas. This is a liquid. Therefore, I can't use 22.4 liters on this substance, but I can use it on these just fine. How many liters of chlorine will be needed to make 75 grams of C2H2Cl4? So, how many liters of chlorine? 75 grams. I know I have 75 grams C2H. Let's go ahead and change this to moles. 1 mole. And this is sort of where you get yet again in touch with your inner Bob Ross, and you can just start flowing through these problems. Go to the periodic table, add up the molar masses of carbon, hydrogen, and chlorine, and you will get 167. Luckily, I already did this, so I have it on a paper next to my computer. 54 grams. Okay, let's do our molar ratio. This is 1. Yet again, remember, make sure these are always balanced. This was already balanced, but don't forget that step. And I'm going for liters of chlorine. So 1 to 2. Two moles of chlorine gas. But I need liters. If I stopped right here, I would have moles of chlorine gas. So I know 1 mole of chlorine gas is equal to 22.4 liters. So essentially we have grams, we're given a mass, we're going from mass to moles to moles to volume. And do our units cancel? Moles, 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 liters of chlorine, which is what I want. How many liters of chlorine? So if I do this math, I'm going to end up with about 20 point, well, about 0.2 liters of chlorine gas. I already kind of did my math before, so I could save that time. Okay, last question. Yet again, they want to be tricksters. This is a solid, this is a gas, this is a solid. So we have calcium carbonate, CO2, carbon dioxide, and calcium oxide. How many grams of calcium carbonate will I need to form 3.45 liters of carbon dioxide? Well, let's put 3.45 liters of CO2 and convert it to moles. 1 mole CO2 equals, and this is a gas, so I can use my liters, 22.4 liters of CO2. Okay, I need to construct my ratio. I'm going from carbon dioxide. Trust me, I've messed up this step. It seems so easy, but sometimes you misidentify things, you're not paying attention, and then you make a mistake and get it wrong. So 1 mole of CO2 is equal to 1 mole of calcium carbonate. So we really don't even need this step in here because it's 1 to 1, but I like to do it just because it makes me feel better. And it looks nice. Now, I need grams. I need my answer in grams of calcium carbonate. Well, 1 mole of calcium carbonate will equal about 100.088 grams of calcium carbonate. So yet again, I went from volume to moles to grams. And if I do that math, I get about 15.4 grams of calcium carbonate. Whew. All right, well, I feel like that was a good lesson. We definitely had some good practice on volume to volume stoichiometry. And we're just going to continue doing more stoichiometry and practicing more until we just get better and better at it. So thank you for watching the video, and I hope that helped. If you have any questions, let me know.